Hello everyone. So in this video I'm going to present the second part of the introductory session. I'm going to show you the example of the standard deviation method. How do we use the standard deviation method using Excel? Also I will talk about linear regression. I will show you an example to find the slope using Excel also, and how do we check the accuracy and the precision of our results. Let's go again to this example, the example of the six velocities. When we have measured the velocity of an object 6 times, we did the calculation using a calculator on a statistical mode. Okay, now we are going to use the same values, but to do the calculation using Excel. So here it's a prepared Excel sheet, number of trials 6. Here we have the values. Excel can give us directly the average and the standard deviation. So similar to the calculator, we can directly obtain the average and the standard deviation, and from the standard deviation we calculate the RMS error or alpha RMS. Also using Excel we can do the same procedure. So fx, we introduce our function, so average. Okay, here I'm using the average frequently, so that's why it's at the beginning of this table. If you cannot find it, you can search here. So you can type here average and you will find it. So I need to select my data. Okay, so the average is 3.510. So here I'm already using the expected decimal position. You can increase or decrease the decimals using this function. So here I'm increasing the number of zeros, or I can decrease the number of zeros. Now regarding the standard deviation method, also function. As you can see here, STDEV is the standard deviation. So okay, again I select my data. Okay, so the standard deviation is 0.021908, etc. Now regarding the error, equals to the standard deviation divided by the radical of n. N is the number of trials, so square root. How many trials do we have? 6. So the error in my case, it's already rounded. Let's say the obtained error is 0.0089. If I'm doing the rounding manually, I need to check the first significant digit and do the rounding. Using Excel, you can decrease the number of digits, and then we round the value to the same decimal position. Here we have the same decimal position. So this is the way to use Excel to find the average and the error on the average. Now, let's go again to our presentation. If we have also an experiment, we did our experiment, but we have 2 variables. So instead of having 1 variable, I have 2 variables and I have a set of data. So I have like 2 related value or 2 related physical quantity. I'm trying using linear regression to predict a linear relationship. Okay, linear regression, linear stands for a straight line. So every time I see a linear relationship, I think about a straight line. Okay, regression, I'm trying to predict a theoretical curve, and this curve should be a line, and this theoretical curve will describe the relationship of between my data. So I have 2 variables. I'm changing a variable. After changing a variable, I'm measuring another one. So I have a dependent and an independent variable. The independent variable is the one that I'm changing. So I change the length and measure the speed. I change the mass and measure the weight. I change the incline and measure the acceleration. So the independent is the one that I'm changing. So after changing this variable, I'm going to measure another physical quantity. So this physical quantity will be affected by the change. It will be the dependent variable. If I want to describe this in a equation, the independent variable is x, the dependent one is y. So every time you are plotting, it's y versus x, y as a function of x. So after changing x, I will obtain a change on y. If I don't change x, y will remain the same. So how do we represent it? Y equals a plus bx. A is the y-intercept and b is the slope. Okay, it should be a straight line. So here, as you can see, the blue line is my predicted curve, the theoretical one, and these red dots are the value, the actual obtained value. Okay, so we need to use Excel or our calculator to find the slope and the y-intercept. Also, using the calculator, we can obtain what we call the correlation coefficient. So the correlation coefficient will give us an idea about the relationship between our two variables. If r is 0, in this case there is no relationship between the two variables. If it's close to 1 or to -1, so the closer to 1 or -1, the better the linear relationship. Now in this example, I'm showing you the weight and the mass. Okay, I will, let's say the experiment was, I was changing the mass and measuring the weight using a force sensor. So our independent variable is the mass. So if I did not change the mass, I will not obtain a change in the weight. So m is x and the weight is y. Every time we need to use linear regression, we start by y equals a plus bx. Y is the weight in newtons, x is the mass in grams, the slope it's y over x. Of course, we are not going to do y over x. Why I'm writing y over x? To show you that the unit of the slope is the unit of y over the unit of x. The slope, using your calculator, we are going on the statistical mode to directly obtain b and a from the calculator. So the unit of a is the same as the unit of y because it's the y-intercept. B, it has the unit of newtons per gram. So for example, I can directly ask you to find the gravity. So based on omega y equals mg, so g is the slope. Or I can ask you what is the physical meaning of the slope. So I can ask you to find the slope and then ask you what is the physical meaning of the slope. So based on the theory, we know that w equals mg. Okay, m is x, w is the weight, so g is the slope. Okay, or based on the unit, we can convert it to the SI unit and obtain the physical meaning of this slope. Now, how can we do this using Excel? It's very easy. Also, I have prepared an Excel sheet. So we have m, the weight, the mass, w is the weight. Okay. We have also a function. It's called the slope. You will obtain, you will need to introduce your y and your x. So for the y, I select my data. Also for x, I select my data. And I have obtained directly the slope. Now, if we check the values in the table, okay, we have 3 significant figures for the mass. If we go again to our representation, it's 100 point, 200 points. So I'm considering the zeros to the right. So 3 significant figures, 3 significant figures. It's a division, so we need to round it to the least precise number, 3 significant figures. We round it to 3. It's already rounded to 3 significant figures. How do we increase or decrease if you have forgotten? By using this this part, the number one. Okay, how can we find the y-intercept? The y-intercept, intercept. And again, I select the y variables and the x variables. Okay, so it's minus 0.06. Now, regarding the plotting. Okay, usually every time you have a linear regression, you are going to be asked to plot a graph. So we select our data, insert, and you can pick the way you want the values to be represented. So if we pick this one, as you can see, you can add, we need to add the titles of the axes. So here the x title is m in grams, here it's the weight in newtons. And also we can obtain the y-intercept and the slope directly from the graph. We add a trend line, right click, add a trend line. So my expected relationship, it's linear. If I try another one, it will be shifted. So we have a linear relationship, and we can directly add the equation on the chart. And in this way, we have obtained y equals the slope, which is 0.0099, x minus 0.06. So every time I ask you to plot a graph, you need to use Excel, and simply you copy and paste this graph to your lab report. Now, if we go again to the experimental work, or to the discussion of accuracy and precision. So accuracy, it's whenever you have a close, you need to check how close the measured value or the reported value, how close it is to the literature. Or for the precision, we need to check delta x. Now, to check the accuracy, we need to report the percentage error, which is the difference between the measured and the theoretical value over the theoretical value. Of course, it should be in absolute value. If the percentage error is less than 10%, our results are acceptable. Less than 5, accurate. Less than 2, they are considered precise. Okay, we can mention that they are considered precise. For the precision, you only find the precision whenever I ask you to discuss the precision, or you see directly the word precision or precise on the question. But whenever I ask you to compare, you need to find the percentage error. After finding a percentage error, you need to comment. Okay, so it's not enough only to find the percentage error. You need to comment. Are your results acceptable? Are they accurate? They are precise? Okay. Let's go again to the example of the gravity. The theoretical value is 9.81 meters per second squared. A group did the experiment. They have obtained an experimental value of 10.7 meters per second squared. Percentage error, it's 9.07. It's acceptable but not accurate. Okay, another group or another experimental work, we have obtained 9.42. Percentage error 3.98. It's less than 5, so it's acceptable and accurate. Okay, so we need to add the comment. Are your results acceptable or they are accurate? Regarding the precision is discussed based on the relative uncertainty, which is the ratio between the error and the average, or the experimental value, times 100. So if we go again to the example of the speed or the velocity, alpha over x, so 0.009 over 3.410 times 100, it's 0.632. We have a very small relative uncertainty. Our results are precise. Now, even if our results are precise and accurate, we need to think about the sources of error. What do you mean by the sources of error? At the beginning of this introductory session, I have mentioned in the previous video that we cannot totally control the experiment. We are going to obtain a slight shift between the expected value and the obtained value. So we have what we call the systematic errors. So these errors are directly related to the experiment itself. So the instrumental error, they are related to the setup. So this error will vary from one experiment to the other one. So if I'm doing a free fall, I need to check my setup. It can be, the error can be related to the detector, to the object. Okay. If it's a motion on an incline, the error will be related to the track, to the cart. Observational is the recorded value, so it's due to me. We can try our best to reduce these observational errors, but it will vary from one person to another one. The environmental errors, it's caused by the surroundings. So let's say I'm doing the experiment on the lab, and I'm neglecting let's say, I'm neglecting the temperature change, the fluctuation. Okay, so these, I cannot remove these errors. Okay, I need to work, for example, in a clean room, or if I'm doing an experiment in vacuum. Okay, So the environmental error is everything related to the things surrounding the experiment. The theoretical one are related to our approximation or to the given value. For example, the gravity it's 9.81, but it's an approximate value, an average value, it's not the exact value of the gravity. Okay, so these errors, we cannot simply remove these errors. Okay, and they will be different between, they will differ from an experiment to the other one. Now the random error can be reduced by repeating the experiment. So if I repeat the experiment, of course a precise experiment, I can increase the precision of my reported value, and by increasing the precision of my reported value, okay, I can reduce the effect of the random error on my values. So what you are going to do every time you are going to discuss and to think about the sources of error, and while preparing your report, every time I ask you to list your sources of error, you need to list at least 3 sources of error. So that's it for the introductory session.